Okay, good morning, good afternoon, everybody, wherever you may be. I hope that people can hear me. I will check in the chat to see if there's...
Yes, we can hear you.
Yes, fantastic. Thanks. So look, sorry, I've just come over from the other session, but we'll get started on time. We do have only 2 speakers in this session, so we have a little bit more flexibility than in some other cases. But I just wanted to welcome everybody warmly to the session. The talks are in the broad area of gravitational wave data analysis and sort of detector characterization. And as I said, we have 2 speakers. Please don't hesitate to put your questions or comments into the chat box during the talk or at the end. And also, please don't hesitate to raise your hand if you have any questions for the speakers. Yesterday, I had to remind everybody for GW1 that we must stay on time, but this session is a little bit more flexible. So I guess we'll get started. Andres, have you had... Oh, and before we begin, I want to thank very much Liam Dunn, who held the fort as the session host while I was giving my talk in the other session. Andres, do you want to share your screen and start your talk, please? You'll be speaking about the search for Scorpius X-1.
Yeah. Right, so can you see my screen?
I can, thank you very much.
Okay, good. So, well, hello everyone. Thank you for being here. I'm Andres Vargas from the University of Melbourne, and today I'll be talking about the search for gravitational waves from Scorpius X-1, the 3rd observing run of the LHC. This is on behalf of the LIGO, Virgo, and KAGRA collaboration. So the talk will be divided in 3 parts. First, I'll go through a very brief introduction, which by this point I assume you all will know very well. Then I'll go through the pipelines we're using for this search. And finally, I'll show some results of previous searches. Right, so gravitational waves are ripples in space-time generated by accelerated masses. They offer a new avenue to study the universe, which is complementary to the electromagnetic spectra. We have already detected a type of them, but we're interested in the continuous gravitational waves for this search, or CW for short. So as their name suggests, these are waves that are continually being emitted by a source, and although there might be many channels for this to happen, a simple one is just to consider a bump in a neutron star, and this will be dragging space-time with it as the star goes round. The thing with them is that the gravitational waves are being emitted at a multiple of the star's spin frequency. So if you know the star's spin frequency, you know where to search. And well, there are many good sources for them. For instance, yesterday we saw one about supernovae remnants by Lucy Strang. There's also low mass X-ray binaries, from which Scorpius X-1 is part of that family, and well, many more. So in general, low mass X-ray binaries such as Scorpius X-1 are binary systems composed by a donor which accretes matter onto its companion, which is generally a compact object. And the thing is that if we believe that gravitational waves are the mechanism to spin down these sort of systems, then we can show that the strain of these gravitational waves is proportional to the square root of the X-ray flux. And therefore, Scorpius X-1, which is the brightest LMXP in X-rays, will be an ideal candidate to search. The thing is that we don't know the spin frequency of Scorpius X-1. So if we want to search for it, we will have to go through a broadband, and these obviously will increase our computational cost. And apart from this, we know that the spin frequency of LMXPs can wander stochastically, which makes the search more difficult. For instance, for Scorpius X-1, the time scale for this frequency wandering has been estimated to be around 10 days. So this also has to be added to our model. So well, the data we plan to use comes from the LIGO observatories in the United States. These are L-shaped facilities where a laser is being pumped into two cavities. And in practice, when a gravitational wave passes through these, it will stretch and contract the arms, and that will create a certain interference pattern here in the output port, and that is the data. So we plan to use the third observing run, which started on the 1st of April 2019. It's divided into half. The first half finishing the 1st of October 2019. There was a month of the commission, and then it started back in the 1st of November, and it went up to the end of March. It was cut short due to the COVID pandemic, but still it's the longest search that has been run by LIGO, which is very exciting. We plan to use both halves in our analysis. So well, now that we know the introduction, I'll go through the pipelines we're using. So the first one, the Viterbi search, which the lead analyst with Pat Meyers. In the search, the pipeline considers a hidden or unobservable parameters as steps of a Markov chain related to the observable states through a probability, which means that we're considering the gravitational wave frequencies as the hidden parameters. The observable states would be the data, and we have a statistic that links these two. So the hidden gravitational wave frequencies tracked through a trellis of log likelihoods that come from a statistic, which I'll explain in the next slide. And we do this for blocks of duration t drift. We choose t drift to be 10 days to coincide with the time scale of the spin wandering. And we assume that the gravitational wave frequency can vary at both a frequency bin, which is related to the inverse of this t drift, for every block of 10 days. When we have all of this set up, we use the Viterbi algorithm to efficiently track the highest log-like path that follow all of these assumptions. And here to the right is a little diagram of how it will look where it's plotted the signal path against the optimal path recovered by the Viterbi algorithm. So the statistic we use is called the J statistic, and it converts the interferometer data into the likelihood that a signal is present at a frequency f. It takes into account various parameters of the binary system as the projected semi-major axis and the orbital phase at a reference time, as well as the period of the orbit. And how does it work? Well, here I show two statistics. One is the F statistic to the left, which takes into account the Doppler motion due to Earth rotation and motion around the solar system barycenter. And it's really good when you have an isolated source. But the data here used comes from a binary, or mocks a binary rather. And you see how the F statistic shows a modulation and a bit of a forest structure over here, which has to do with the fact that the signal is being Doppler shifted to the motion of the binary. Meanwhile, the J statistic takes this into account, and I add the orbital sidebands appropriately, and therefore returns a higher peak, which is very clear compared to the other data. So as this statistic takes into account the orbital parameters, and these as well have some uncertainty, we have to look in a parameter space. We do this by using a grid, which you can think a bit of as a fishnet. And a lot of our computational expense goes in trying to go through this space, as the number of templates we have to search depend on the frequency. So the higher the frequency, the more points in this space we have to search. Now, finishing this pipeline, a little bit of what the hidden Markov model tracker is. So in general, we will divide our data in 10-day chunks, which are each of these columns. And each column will have some frequency bins, which are these boxes. And each box will have a number in it that comes out of the statistic. And hopefully, the higher the number means that it's more probable the frequency of the gravitational wave will be there. And here it's marked as F star. And what the Viterbi algorithm does is that it returns us the path where with the highest likelihood that accommodates for the signal jumping one of these boxes or staying the same or going down, which hopefully should be the path that the gravitational wave will have. Here is another example of this where we have several time steps and several frequency bins. A signal has been injected. And here we see in blue the true signal that was injected, which is wandering around, and the green, that is the recovered path. At the beginning, we see they don't match exactly, but as time goes on, it comes very close to it. And here lies the true power of this algorithm, as with more time, it's more likely to follow the true signal. That's why we are very excited about this search, or rather, sorry, this run, which is the longest that has ever been done by LIGO. Now, the second pipeline that we are using in this search is cross-correlation, and the main analyst is John Willem and his team. And in this, the data is divided into chunks of TSFT, and these SFTs are used to construct a cross-correlation where each SFT has to is constrained by this time relationship. That is, they have to be separate by a time lower than this Tmax, and Tmax is a free parameter of this pipeline. The statistic is constructed using this equation where set I and J are normalized SFTs and W is a filter function. So as I say, Tmax is a free parameter, so it can be chosen at will. It can be increased, and with this, you're taking into account more SFTs, which improves sensitivity, but it also comes with a higher computational cost. So it has to be balanced, sort of a cost-benefit situation. And here to the right is a little diagram of how these constraints will look. The SFTs can be from the same detector or from different detectors as well. So this search also has to go through the orbital parameters of our system. So also takes into account A0, the time of ascension, and the orbital period, which also means that they have to go through various templates, and this adds additional time. But there have been new implementations, such as a more efficient lattice placing, as the one we see here to the right, where all of these templates have been changed for just one line over here. And also the application of a resampling code, which decreases the search time, especially for the lower frequencies, which means you can have a higher Tmax and therefore get more, have more sensitive results. So with the two, well, after the two pipelines, I'll go a little bit, I'll talk a little bit about the searches that have been done up to now. So waves from Scorpius X-1 have been searched in all three of the observing runs. In the first one, we had radiometer, Viterbi, and cross-core. In the second one, we also have radiometer, Viterbi, and cross-core. And the cross-core analysis was done by the group at the Albert Einstein Institute. And the O3, the result, we have the results of the radiometer, they're out, and we're still doing the search. So to end, I'll explain briefly some of the results we have up to now from all of these searches. So here I'm graphing the marginalized upper limits, frequentist upper limits. These are obtained by doing many injections into the data and trying to recover those injections. So it roughly translates, if you inject a signal with this strain 100 times, you will recover it 95% of those. So these results are marginalized over the inclination angle of the system. So we see how each of them compare. We have in green the Viterbi 02, in black the cross-core 01, and the results of the radiometer as well. And in brown, we have the results of cross-correlate 2 and how all of them compare to the torque balance, which is what we expect theoretically for the strain to be, or in what area roughly we expect it to be. So with these values can change depending on other assumptions. For instance, instead of marginalizing over the inclination angle, we assume the astrophysical priors. They can shift a little bit, and actually in that regime, the cross-core O2 results deep under the torque balance, which is pretty exciting, but I won't spoil the talk of Shang on Friday. So yeah, we hope that for O3 we'll have results that will go under this torque balance. And yeah, I guess it's an exciting moment to see what happens with this search. So yeah, that was my talk. I'll take questions.
Thank you very much, Andres, for a very clear talk. Excellent. Are there any questions for Andres, either in the chat or with the blue raised hand, if you would? Thank you.
Hi, Andres.
Yes.
Oh, hi, I'm Harry. Hey, nice talk. Thank you. So in the abstract, I saw the discuss projected sensitivity for the search using LIGO O3 data. So I suppose it's not a time.
Yeah, sorry, I didn't add that.
Okay, anyway, I'm very excited to see this. Thank you.
Sure, thank you.
Thank you very much. Fernanda, do you have a question? Is that why you're unmuted? No? Okay. Good. Well, we do have a few more minutes, but I'm checking the raised hands in the chat, and there doesn't seem to be any further questions. So I guess in that case, we'll thank you very much again, Andres, for an excellent talk. And the next speaker is Pat Myers, and we do have him online. He will be speaking about correlated magnetic noise across different interferometers and the way that affects our prospects of detecting stochastic background. Thank you very much, Pat.
Thanks, Andrew. Can you hear me and see my screen?
Yes, very clearly.
Okay, fantastic. Yeah, feel free to cut in if I run long. Hopefully I'll stay on time. Okay. So thanks for giving me the opportunity to speak here. I'm going to talk about discriminating between a gravitational wave background and correlated magnetic noise, specifically with LIGO and Virgo-like detectors, so ground-based detectors. So when we talk about stochastic background, we're talking about something that is long duration, and the signal is poorly modeled. Whereas, for example, by contrast, something like CBCs would be short duration of order minutes and very well modeled, so that you have something that you can use for matched filtering. The stochastic background is persistent, but very poorly modeled and is assumed to be essentially colored Gaussian noise. So there are two broad categories when we talk about the gravitational wave background. We talk about sort of broadband persistent gravitational wave signal whose waveform sort of by its very nature is not deterministic, and that would be something on the right here that looks sort of like just Gaussian noise, and that would be something like gravitational wave background from the early universe or inflationary models. But you could also have a collection of deterministic signals that are not individually resolvable. And that would be like something like binary neutron stars or binary black holes that are too far away to be individually resolvable. And so you could imagine, say, this plot down here being sort of swamped by noise, and the cyan, which is the binary neutron stars, and the purple, which are the binary black holes, sort of popping off every once in a while and giving you a burst, but you can't necessarily see them individually. And so their superposition gives you some sort of background hum that adds up to something that is effectively Gaussian. You could also have other potential unresolved examples, but binary systems are what we expect to dominate and almost certainly dominate any sort of early universe models as well. So the stochastic background is usually characterized by the dimensionless energy density, which is the energy density in gravitational waves per logarithmic frequency bin, which is why we have this F over dF. Normalized by the critical energy density to close the universe. So sort of similarly to a lot of the cosmological parameters that you might see. And this is often characterized by a power law, where you have some amplitude of the stochastic background at some reference frequency. So the amplitude is omega at some reference frequency f ref. And you have the some power law with a spectral index alpha. And alpha is equal to 2/3 for a gravitational wave background dominated by unresolved binary inspirals, like from binary neutron stars or binary black holes, which is what we expect to dominate our background. And there was a talk yesterday by Mary Sakallariadou in the Gravitational Wave Sources Block 1 session that goes through this in quite a bit of detail, the sorts of physics and things that you can constrain using the stochastic background. And the way that we search for these things, because there's not a well-defined signal for the stochastic background, is that we cross-correlate data between different detectors. So we can construct this C hat of F, where S1 and S2 are the Fourier transforms of the data streams in detectors 1 and 2, and it's normalized by tau, which is the time over which those Fourier transforms are taken. And you can take the data from S1 and you can write it as a sum of some gravitational wave signal and some noise in the detector. And now you can substitute this in, and you can take an ensemble average, and you can get this sort of list of 2-point functions here. And you have something that contains gravitational waves in this first term. You have something that is noise, correlation between noise and gravitational waves in the second and third terms, which should go to 0. And you have some term that looks like the correlation of the noise in detectors 1 and 2. So typically what we do is we assume that all these last 3 terms go to 0, that the signal and noise are uncorrelated. That's something that I really hope is true. And the noise is uncorrelated between the different detectors. And then you have some gravitational wave background signal. So if you average over many, many times, these 3 terms go away, and you're left with C hat converging to something that's proportional directly to the gravitational wave background. But this last thing is not necessarily true. The noise is not necessarily uncorrelated between the detectors. And so we want to know at what level do we expect this to break down? And in the future, if we run into this correlated noise, how are we planning to deal with it? So the correlated noise that I'm going to speak about today is correlated noise from sort of globally coherent magnetic fields. I have an extra slide on some other potential correlated noise that comes up in our detectors if you want to hear about that. But in this case, we're going to talk about Schumann resonances, which are the sort of the eigenmodes of the Earth ionosphere resonant cavity. So they're excited by lightning strikes all over the Earth. And what you get are peaks in the magnetic spectrum at say 8 Hertz, 14 Hertz, 21 Hertz, 26 Hertz, going up the band. And all of these are PSDs of different magnetometers all over the world. So Poland, Colorado, Argentina, LIGO Hanford, LIGO Livingston, so on and so forth. And so you can see that first there's a variation in these peaks, but these peaks are common to all of these spectra. Now, if you take a coherence between a magnetometer at LIGO Livingston, which is LIGO1, and say Poland, then you see a spike here or a peak here in the same place as you saw in the plot up above. So the purple is the correlation between 2 magnetometers that are essentially next to each other or very close to each other. The black is what you would expect the coherence here to look like if there was no correlation at all between the 2 signals that you're calculating the coherence for. So you see that we're seeing very strong coherence for magnetometers that are separated by tens of thousands of kilometers. And this is a problem if those magnetic fields couple into our detectors in some way. So if the magnetic fields somehow induce some motion in the mirrors in a detector in Livingston, Louisiana, and one in Italy, then the correlation between those magnetometers or the magnetic fields will imprint themselves on the mirrors. And when you go to correlate the data between those different detectors, you run the risk of having correlated noise and biasing your estimate of the stochastic background. Okay, so how can these low frequency magnetic fields couple into the detectors? If you have some sort of magnets on the mirrors that are used for actuation to keep the mirrors in lock, then those magnetic fields could accidentally drive the mirrors. You could also have electronics. You have lots and lots of cables all over site, and if you get some sort of changing magnetic field that could induce a current in those cables, and that gets into your feedback systems and imprints itself on the mirrors, then you could run into a problem. And so what they do is they measure the coupling function between the magnetic field the actual differential arm motion of the LIGO detectors, the strain data that you measure to do your searches with. So what you have here on the y-axis of this top plot is a magnetic coupling function, so how much our mirrors move in response to a magnetic field of a certain strength in units of Tesla as a function of frequency. And so you can see that it looks like a broken power law generally, the general trend. So this first plot is as a function of time. These were measured essentially every week of the last year of the 03 run for LIGO Hanford and LIGO Livingston and for Virgo. And what we have here is the strength of where this break happens, the amplitude here. We have the first spectral index, so roughly -3 as a function of time. And then we also have the second spectral index, this turnover as a function of time down in the bottom right as well. So you can fit these coupling functions with a broken power law or a power law or something along those lines. But you also have some resonances in some places, which could cause problems in the future, especially if those get louder or you change your detector configuration. So these are all things that we have to keep an eye on. You can construct a correlated magnetic noise budget. So what you can do is you can take those coupling function measurements from the previous slide, and you can take coherence between magnetometers that are sitting next to the detectors, and you can multiply your coupling functions by your coherences, and you can essentially get an estimate of the contribution of correlated magnetic noise to C hat of F, or to your estimate of omega GW, which is what we're really interested in. So we've constructed a budget for the 03 search, and that's what's in this shaded region here. So the uncertainties here in this shaded region, which is quite large, sort of encode in them the changes in the coupling function as a function of time over the course of the whole run. The red is the sort of integrated sensitivity across the whole frequency band of the 03 search for gravitational waves for a stochastic background. So this red should be compared to the general trend of the black and shaded regions down here. And so you can see that we're a couple of orders of magnitude below our sensitivity. So that's good news. We don't expect that this 03 data is contaminated by correlated magnetic noise. Up here is the sensitivity in each individual frequency bin of the search. And so this could be compared to, say, the spikes that you see in these black pieces, and you can see again that this is much lower than these black spikes are much lower than this black curve up here. And so again, we don't even expect to see sort of sharp spectral features in the data either, and it looks like we don't. So that's all good news. So this is how we construct a correlated magnetic noise budget, and it looks like for 03 we're okay. We can also try to estimate parameters and try to estimate the strength of the correlated noise, especially important for future detectors, which will be much more sensitive. So as this red curve gets much lower, for example. And as I said, the current budget indicates correlated noise is not an issue, but we're interested in this for future detectors. So I'll introduce very briefly a method for simultaneously measuring correlated noise in the gravitational wave background. So you can take your C hat of F. This is normalized slightly differently from the one that I showed a few slides ago, but you can think of it in spirit as the same thing. And you can subtract from it some model for the stochastic background, or some model for the stochastic background plus some model for the contamination due to correlated magnetic noise. And what you should get back is, after you subtract this off, is just pure Gaussian noise should be left over. So in this case, you can include a power law model for gravitational waves, and you can include some model for the magnetic, this magnetic budget here. And I'll discuss this on the next slide. So this omega mag is going to be some product of your coupling functions or your transfer functions. The transfer functions include phase. The coupling functions that we talked about before ignore phase. And for now, we're assuming that these transfer functions are real, which is a pretty strong assumption. But it's done to make the problem simpler. You multiply these by essentially your coherence or your cross correlation between magnetometer data at your two sites. So this is a magnetometer at site 1, this is a magnetometer at site 2, and the rest of these things are normalizations to put these in the same units as this omega mag, essentially. So this is a geometric factor, and this piece contains in it different constants and also weights related to the noise in the detectors, the LIGO detectors. But these transfer functions, actually, we're going to allow for now, even though we have coupling function measurements, we're going to allow these to be power laws that have variable amplitude and variable spectral index. And I'm happy to answer why that is, but essentially it's because the coupling function measurements are quite uncertain. So we want to be able to allow those to have some change in them. And that uncertainty is built into the budget, but it wouldn't be built in necessarily out of the box to a parameter estimation method like this. So that's why we parameterize our uncertainty in this way. Okay, so if you put in a very strong correlated magnetic noise signal and you try to estimate it back out using Bayesian parameter estimation, you can estimate the kappa for each of the different detectors for the coupling function or the transfer function for each of the different detectors. And so H, L, and V, and the spectral index for each of the different detectors. And one sort of striking thing to note here is that while Virgo is in this case not particularly sensitive, and it actually doesn't help us measure gravitational waves, it does help us estimate the parameters for our coupling functions in the individual detectors very, very well. And there are a couple of reasons for this, but you can see that the green is if you have only Hanford-Livingston, and the blue is if you include Virgo, and it's helping us with our coupling function with Hanford and Livingston as well, quite a bit. So that's good news. You can also construct a Bayes factor that compares a model that includes gravitational waves and correlated noise to a model that includes only correlated noise. So essentially trying to detect gravitational waves in the presence of correlated noise. And you can see how that Bayes factor scales as a function of time, assuming design sensitivity for advanced LIGO. The orange is if there's no correlated magnetic noise at all. And the blue is if you have a strong correlated magnetic noise signal. The green is if you have a strong correlated magnetic noise signal, and you have very noisy measurements of your magnetic coherences. And you can see that it will increase time to detection, but the general scaling is still linear with time, which is very good news. So it will increase time to detection, but it's not going to hurt you all that much. So we did this, we actually applied this method to O3 data. We found no evidence for correlated magnetic noise in the data. We found no evidence for correlated magnetic noise or gravitational waves in the data. And as I said, this is not surprising. As we saw from the budget plots, we expect it to be quite low. But it's a useful method to keep in mind for future detectors. We need to update our methods for future runs, especially for parameter estimation. The parameter estimation methods don't include these potential resonances that you see, these peaks in the coupling functions. It also didn't include higher frequency coupling function measurements, which is something that a student, Camille Jensen's, is working on. And we also would like to include multiple pairs of magnetometers at separate sites. At the moment, we're just using a single pair. So I'll leave the conclusions there because I've run a little bit over, but I'm happy to answer questions from people. I can't see the chat, so I'll let Andrew field questions.
Thank you very much, Pat, for a very clear talk. That's excellent. So questions for Dr. Myers. Julian.
I had a couple of questions. On slide 12, can you go back to that?
I don't seem to be able to see my own slide numbers. Oh, there it is.
Okay. You're
Okay.
on 17 at the moment.
Yeah, the little box was on top of it. Yes, go ahead.
So the peaks in the black and the black dashed seem to be in the same place.
Yes.
Is that to be expected, or is that some sign of coupling in?
That's, I think, just there are lots and lots of peaks, and so they look like they're in similar places. So some of those peaks are similar things, but actually the peaks in the black dashed are due to a few different things. They're potentially due to noisy magnetometer measurements from Virgo. There were spikes in the magnetometer data at Virgo. They're also potentially due to the fact that this is a bit of detail, but essentially the real part of the complex cross correlation will pass through 0 for the magnetometer measurements in different places than it would pass for gravitational waves between the sites. And what that essentially means is that let's see if I have an equation here. That's essentially this gamma function, and this gamma function will go to 0 in some places and make this thing blow up. And essentially this thing will also go to 0, and it will go to 0 in different places from this thing. So if these were gravitational waves, this numerator would go to 0 in the same place as the denominator, but for magnetometer data, it won't, and so you will actually get those spikes. And so it's a combination of potentially magnetic artifacts, but also sort of this sort of strange feature of the way that this model is constructed. But it's actually quite nice because it gives you actually very useful information.
Mm-hmm. Cool. I had one more question. At the very start, when you say the signal and the noise is hopefully not correlated, is there I could imagine some perverse scenario where when you have a signal coming in your strain data, it excites some noise at the same time. Has that been considered? Is that how do you discard that possibility?
Yeah, it's really funny that I've given a talk like this many times, and I've always said that, and I've always sort of thought, oh, it's not something you have to worry about. And this time, as we went by it, I thought exactly the same thing you did. It's not something that I've ever heard anyone talk about, but I think that probably it's not something that we would expect to see. I think it would be probably some sort of nonlinearity in the control loops that I would not be able to understand. I think it would probably have to be a very, very loud signal, and it would probably be like a very, very loud CBC signal that would cause something like that. And I really don't think it would be something that would be a problem for a very quiet signal like the stochastic background.
Right, and I guess the long integration times might help smooth over those glitchy type correlations.
Yeah, that would be my guess.
Okay, cool, thanks.
Thank you very much. The next question is from Lucy Strang.
Yeah, hi, nice talk. I did have 2 questions, but Julian stole one of them. So I guess this may be a naive question, but you've put all of this correlated noise in the context of the stochastic gravitational wave background. Is there any point where we start worrying about this noise for other gravitational wave signals, or is it simply it's too quiet for us to need to worry about that?
Yeah, so this specific form of noise, yeah, so that's actually a very good question. So for future detectors, actually, this could be a problem. So for Einstein telescope, for example, there's a chance that local magnetic fields will be a limiting noise source for Einstein telescope. So there's a paper called Site Selection for Einstein telescope, where they sort of show the design sensitivities, and they show expected noise for, say, seismic noise and local magnetic fields, and they're very close or over the expected or the proposed design sensitivity. And so for something like Einstein telescope, that's a problem, because actually just even local magnetic fields will then be coherent, because you have multiple interferometers for Einstein telescope in one place. And so you would probably try to do some sort of online noise subtraction and then use this. But that would be a problem for almost any sort of searches that are cross-correlating data between detectors. So things like burst searches that aren't using waveforms, for example. For anything that does some sort of matched filtering, I think this specific source would not be an issue. There are other correlated noise sources that could be, for example, like coherent combs and things like that.
Great, thank you.
Thank you very much. We are at the end of the session. I might just sneak a very quick question in, Pat. Have people done this sort of study from correlated magnetic noise for LISA? Because presumably the solar wind especially, you would expect pretty strong magnetic correlations across the 1 million kilometre baselines that ELISA would be looking at.
That I don't know about. Yeah. Yeah, I don't know the answer to that. That would be interesting though. Yeah, like I don't know what the noise budget looks like for LISA Pathfinder. You would potentially expect that to be a noise source there, but to start with, so it's probably my hunch is that if it's not limiting LISA Pathfinder, then it's maybe not as big of a deal for making sort of short duration detections of things like double white dwarfs, but maybe for longer duration things, it could be, because again, you would eventually run into this issue. But I don't think that anyone has talked about it, but I could be very wrong.
Interesting. Great. Okay, well, look, we are at the end of the session for today. Let me just say 3 quick things. Firstly, a massive thank you to everybody who did come along. Secondly, thank you to the 2 speakers for excellent talks and for sticking to time. And thirdly, thank you very much to Liam Dunn, who was the co-host and kept the technology working. I'll just remind everybody that we've got the next GW1 session on Thursday, starting at 16:30. So for those of us in Australia, an uncomfortable time, but pretty convenient for the rest of the world. So I look forward to seeing you all there. Bye-bye.
Thanks, everyone.
Now, Andrew, or maybe you can, does the meeting end? Do I end the meeting now, or do I think I just leave?
Yeah, no, I think maybe we just let it run for a minute and then just quit it. Yeah, I had the same question actually yesterday, and I got a short reply from the organisers saying, yes, you can just quit. So maybe we'll just, give them 30 seconds or 60 seconds of quiet time that they can chop. Yeah. And then, yeah. Thank you, Liam. Right. And then we'll be, I guess there are the NS1 and NS3 sessions going on at the moment as well, which will be relevant to some viewers. Mm-hmm.